Hi, I'm Whitney Espick, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
Today, I'm going to talk to you about tornadoes. Here you see a picture of our latest mobile Doppler radar probing a tornado in Kansas. Here's one of my graduate students who's, as they say, outstanding in his field. And give you an example of what we study. Here's a video I took of an EF5 tornado near Red Rock, Oklahoma, almost 30 years ago. And it's just going to give you a feeling for the power and majesty of a tornado close up. Fortunately, this tornado, like most of those that we try to look at, they're over open country, don't do very much damage. There's not that much out there. But you can see the tremendous motions in this tornado. I'll stop talking for a minute and just let you watch it. Unfortunately, I wasn't able to get the camera mounted on a tripod. It was too windy, and we're using a radar to look at the wind speeds in the tornado. And in a minute or so, we're going to ask the question, why did the tornado cross the road? And I hope you can hear the sound of the wind from our location.
The big one, it's not gonna last this way.
So my graduate students are taking a portable radar and they're mounting it outside our van. This is before we had the truck-mounted radar. And the tornado is about to cross the road. I should tell you that we were probably about three miles or so from the tornado. After the tornado crossed the road, we drove down to look to see what was damaged. And only 2 miles away, there were telephone poles lying in the middle of the road. So even when you're not even in the tornado, you have to watch out for flying debris. That was a hailstone hitting the antenna. And the tornado crosses the road, and I think I'll stop it right there. I think you get the picture. This is the tremendous devastation that a tornado can do. These are two panoramic photographs I took in Moore, Oklahoma, back in 2013. And you can see it just looks as if a bomb just totally wiped everything out. It's rather sobering and rather nausea-inducing when you see this kind of damage out there. And we use the damage to estimate the wind speeds. You don't just take an anemometer and walk into the tornado to measure the wind. So you have to have some idea about the structural integrity of the thing that's being hit and so on. The house is totally removed from its foundation and it's well made. It's probably an EF5 tornado. And the weakest tornadoes are rated EF0. Those are those for which there's just very little damage, maybe some minor tree damage. I love the comment over here in this New Yorker cartoon. Here's the television broadcaster saying, but the weather looks great for the rest of the week. This is an aerial view of tornado damage in Moore. And I took this from a helicopter. And the amazing thing here is you can see this 5-block area. Most of the houses are totally destroyed. You look at this row of houses here, and most of them are totally untouched. And you go across the way to the adjacent houses, and they're mostly totally destroyed. And so the horizontal gradient in space of the wind speeds in a tornado are pretty large to go from virtually no damage at all, look at this house, to most of these houses here are just totally wiped out. And the photographs I just showed you, the panoramic damage, were taken within this area. Now, we define a tornado as a, put in quotes, a violently rotating column of air hanging down from a cumuliform cloud that makes contact with the ground. And what do we mean by violently? Well, wind speeds that are high enough to cause damage. Generally speaking, if the winds are 60, 70 miles an hour minimum, that would be considered a tornado. The tornadoes are driven by the buoyancy of the updraft and the parent storm. The source of rotation in the tornado is a very important thing that we try to understand. And the measure of rotation that we use is just what we call vorticity, and that's just the curl of the wind field. And I ask you to remember the good old days of 1802. And you can imagine if you put a paddle wheel in the airflow, will it rotate? If it rotates, there's vorticity. This reminds me a little bit of the David Letterman shtick about will it float? This is a takeoff on that, and it's will it rotate? Vorticity that goes into making a tornado can come from two places. One is it's generated by the parent storm, and this is in a 2.5 to 3 or 4 kilometer wide cyclonic vortex, counterclockwise rotating vortex called a mesocyclone. It's at low levels. It's generally speaking 1 or 2 kilometers above the ground, and they occur in storms called supercells, also in mesoscale convective systems. You know those as squall lines, and mini supercells, rather small supercells in terms of their height, in tropical cyclone outer rain bands. You know that in the outer rain bands of hurricanes, when they make landfall, you frequently get tornadoes. Or they can occur along boundaries where there's pre-existing vorticity and the airflow is coming in from different directions. And these are what are called non-mesocyclone tornadoes that come from ordinary cell thunderstorms as opposed to supercell thunderstorms. And I've given the name land spouts to them, which is kind of stuck, though some people hate the name. I'll tell you why in a moment. This is how the non-mesocyclone tornadoes form, the land spouts. They occur along boundary where there's a shift in the wind and there's shear in the wind. If you will put a paddle wheel in the flow here with the axis oriented vertically, you would see that it would begin to spin like this. And if you trigger a buoyant cloud over that, what happens is you get an updraft into the cloud, and the air must come from somewhere into the updraft. It converges from all directions, and it's conservation of angular momentum. It's like a skater bringing his or her arms in, and it spins up, and you can get a tornado. When I first saw one of these, it came from a storm that wasn't even producing any rain or thunder, and I was amazed by it, and it looked just like the weak water spouts that I've seen over the Florida Keys. So in sort of a reverse thing here, we called tornadoes over water spouts. The water spouts that I had seen were extremely weak. So since these tornadoes were extremely weak, I call them land spouts, water spouts over land. And people hate me for that. Here's an example of a land spout, which I took when I was about to board a Southwest plane at Denver International Airport. And there you see the rotation in the cloud above and the dust column. And this went right over a runway. And they blew the tornado sirens and tried to hustle everyone into the shelter, except for me. I stayed by the window. Security guards kept on trying to get me away from the window, and I refused. So I was able to get pictures and videos. This is a water spout, tornado over water. I took this from a helicopter down the Florida Keys, and you can see how remarkable this is. Here's the condensation funnel, very, very narrow, yet it goes all the way up to cloud base, and you can see the spray in the ocean below. Beautiful phenomenon. These are relatively safe. People have taken their boats through them, and people have flown airplanes through them. They're relatively weak, usually. Oh, sometimes they do make landfall. I know about a week or two ago, one made landfall, and then it becomes a tornado and can do significant damage. Now, two types of thunderstorms. One of the ordinary cell thunderstorms, the garden variety type, in which there's no vertical wind shear. The wind doesn't change with height. And you somehow get the storm going. You get a buoyant updraft. Air goes up, and as it goes up, it expands. It does work in its surroundings. Thermodynamics happens. It cools, and it may become saturated. You get a cloud, and then you might get rain from the cloud droplets. And the rain acquires weight. It has a terminal fall velocity, and it falls out of the cloud. And if it's unsaturated under the cloud, well, it hasn't rained yet, so it's probably unsaturated. Then it evaporates, it cools, becomes dense, and it accelerates further downward. It becomes negatively buoyant. It hits the ground. It spreads out as a gust front. The pressure under the cloud is higher than it is outside the cloud because the air is relatively cool and dense. Its weight is more, so it spreads out as a gust front. This is one of the basic building blocks for all convective storms. And when this happens, the cell usually dies out after about 40 or 50 minutes. And if you sit down with an envelope and a pencil and figure out how long does it take air to get up to the top of the storm and then fall back down to the ground, it's about 40 or 50 minutes. Supercells are very special storms. They rotate, they have a rotating updraft, and they're long-lived. They last for a lot more than 40 to 50 minutes. They last for a lot longer than it takes air to go from the ground up to the top and then collapse back to the ground. They're like the Energizer Bunny, they keep going. And one of the reasons why they keep going is that there's vertical wind shear. So here's a diagram of the winds in the environment of a supercell. In this case, they may come from the east at low levels and from the west at high levels and be very strong. And what happens is, if you put a paddle wheel in the flow here, it's going to start to spin like this. That represents vorticity, horizontal vorticity, like that. All right. And it turns out that if we have an updraft, that if we look at this line, which is called a vortex line, that's a line along which the vorticity is a constant. It turns out that that vortex line gets deformed so that we get counter-rotating vortices. This one rotates in a counterclockwise direction, cyclonically in the northern hemisphere, and the opposite over here. The rain falls in between. Underneath each of these two vortices, we have regions of low pressure. I'll explain that in just a few minutes. But because of that low pressure up here, we have an upward directed pressure gradient force that triggers new updrafts. And the new updrafts then cause the storm to split. And what happens is the updrafts move normal to the vertical wind shear away from where rain falls out. And so the storm's able to last for a long time. This is the most complicated figure in the world, and I only want to show you one thing here. In the previous figure, I showed you how we can get the counter-rotating vortices aloft, but tornadoes occur at low levels. We need to get a low-level mesocyclone going. How do we do that? At the ground, there's no updraft. So what happens is we have the anvil and the storm. That's the upper part of the storm near the tropopause where the buoyant updraft dies because it's a lot warmer in the stratosphere potentially than it is in the troposphere. And if that's the upper level wind, it carries the precipitation downstream and it falls out. And that falls out, the rain falls out and it cools, and you get this cold pool of air in here. And that's adjacent to the ambient warm air outside. Now, if we imagine, if we put a paddle wheel in here with a horizontal axis like this, we have negatively buoyant air in the cool side. In the warm side, it's neutral outside the cloud. So what happens is buoyancy forces air down in the cold pool. Nothing happens in the warm pool. For this paddle wheel, it feels a downward force in the cold pool, no force out here, and it begins to rotate like that. It acquires horizontal vorticity. And in a supercell with a strong vertical shear, there's strong storm relative flow. The air relative to the storm comes right into the updraft and it gets tilted upwards. And that produces this low-level mesocyclone. And that's very important. And there's a Goldilocks thing going on here. We have to have the proper balance between vertical wind shear and the strength of the cold pool in order to get this low-level mesocyclone, which then produces the tornado. This is why not all supercells produce tornadoes. In fact, very few of them do. Maybe 10 or 20% of them actually produce tornadoes. In order to get this horizontal rotation, it has to be cold here. It can't be no cool air at all. There has to be some, but there can't be too much cold air, because if there's too much cold air, what happens is this boundary moves away from the storm and we cut off the warm air flowing into it. The shear can't be too weak, or we don't have enough storm relative inflow. If the shear is too strong, the storm relative inflow is so strong that as the air comes into the storm, it doesn't have enough time to acquire horizontal rotation about a horizontal axis. So we have a fine tuning balance between the wind shear and the strength of the cold pull. Here's a picture I took this last April. Because of COVID, we could not take our radar out. And so, of course, I just drove 1 hour from my house, saw a tornado. We didn't have the radar there, but there you see the tornado in relation to the whole supercell. See how small the tornado is? That is the mesocyclone. And then this is the major updraft. And you see there are bursts of updraft all the way up to the tropopause. How do we study a tornado in captivity? Well, there I am at NCAR with a little simulator trying to get my hands around one. And of course, this is a New Yorker cartoon I love. It says, Amy, Mr. Stoklasa has caught a tornado. And there's that poor guy up in the air. Hopefully that's not us. Back in the olden days, before we had the radars, we would go out with 16 millimeter movie cameras, take movies of tornadoes, and look for debris and try to track the debris. Well, there's a tornado in the Texas Panhandle, and you can't see any debris. Then I decided, well, let's go ahead and try to make in situ measurements. Let's take an instrument, place it in the path of a tornado, let the tornado come over it. We can make measurements that way. So there's an instrument that we call Toto. Of course, after Dorothy's dog in The Wizard of Oz. The acronym stands for Totable Tornado Observatory. And this was a rather, I coined this phrase at a rather drunken cocktail party once with my colleagues. And by the way, in case this looks familiar to you, this was named Dorothy in the movie Twister. They took one of my scientific papers based on the data we collected and called it Dorothy. And of course, we got no credit in the movie for this whatsoever. By the way, this was rather unsuccessful. This tornado, which was doing millions of dollars of damage in Southwest Oklahoma over an Air Force base, came towards us, dissipated before it got to the radar. Another tornado formed, and it moved in the opposite direction, off to the northwest. Very frustrating. So we decided that it would be better to use a radar out in the field. And so back in the late 1990s, we used the first portable radar. For those of you that know anything about radar, it's a continuous wave, frequency modulated continuous wave, X-band radar, and it's from the Los Alamos National Laboratory. And as I understand, it was originally used to track helicopters near the border. And I'm not supposed to say anything else about it, but they wouldn't tell me anything else. But it's a bistatic radar, one antenna from transmitting, one antenna for receiving. You scan it manually, and it's solid state, 1 watt, way ahead of its time, because now we're using these radars again, and they're being put on satellites because they're lightweight and low powered. And for those of you that have a double E background, when you mix the transmitted signal with the received signal, it turns out you measure the Doppler shift, and that turns out to be in the audio range. So we just recorded the signal on a simple analog tape recorder, and then we would take the tape recorder back in the lab, digitize it, take the fast Fourier transform, and voila, we would get the velocities. I'd like you to note that the students are between the tornado and me. And also this made the cover of Time magazine. When Twister came out, they used my photograph of this on the cover. And I really got a kick out of that. Now I want to demonstrate how the evolution of a tornado is very rapid.
Here's a little suction vortex.
This is a tornado that I took, a video I took several years ago, recently, and look at how fast things are happening. helical updraft over here. That's another one over here, another one over here. These are tornadoes within tornadoes.
You ought to be getting great data now.
This is a multiple vortex tornado. I hope you can hear the commentary. But these are individual mini tornadoes within the broader circulation. This is condensation, not smoke. So the pressure is low enough to get condensation.
It's going to be a big one in a minute.
Oh, that's the main tornado funnel.
We're going to leave.
Starting to form.
Debris in
There's
the air.
debris in the air.
Oh my God.
You sometimes see what look like birds flying, and they're usually big pieces of boards and roofing and so on. Tornadoes changing in the order of seconds here. Rather remarkable.
Okay, we've got to go. I'm sorry. I think it's not safe anymore. We've got to go. Shut her down. You get a multiple vortex tornado.
We're collecting data, but we have to move because the tornado is coming towards us. And it takes time to unlevel the radar and shut it down. There goes the storm chaser, I think.
Are we unleveled? Yes. Okay, so we can move? Yes. Yeah, I think we ought to. Yeah, Jana, you still collecting data? How far is it away? How many? Okay, hang on just a little bit longer. Keep collecting.
My graduate student at the time, Jana, wanted to go, and I was trying to hang on a little while longer. So now we have a regular tornado. When this tornado went on, unfortunately killed some people just to the east of where we were in Shawnee, Oklahoma. This is the time-lapse video. Actually, it's a video I took speeded up, so hold your ears, of the dissipation of a tornado. Notice that a lot of it's horizontal. Up in Kansas, and I always like to. It's pretty to look at. Tornadoes during their dissipation part of their life often look like ropes. So scientific motivation, we have the broad questions. What's the source of vorticity in the tornadoes? Why do they sometimes form but most often don't? At what level do tornadoes form? And how, if at all, do they propagate up or downward? Do they begin up in the storm and then build down to the ground? Do they start at the ground and build up? Somewhere in between? Also, what happens when a vortex interacts with the ground? And we have to worry about the behavior of the boundary layer. Major methods of addressing the problems include observations using Doppler radars, which is what I do, idealized numerical models, including numerical modeling of vortex chambers. People used to use vortex chambers. Now we can numerically model the vortex chamber. These are problematic because they look at vortex behavior, but the vortex isn't connected to a storm. You can totally control the vortex. It's like trying to study your thumb without studying your arm. Another way of studying tornadoes is to use observations assimilated into numerical models. Right now, we can make good numerical models of tornadoes, and we can make good numerical models of storms, but trying to model an entire storm using the spatial resolution that will actually resolve a tornado is possible, and a few people have done it, but it takes a lot of computer time, and it's something that's going to become more and more useful as computers get bigger and faster. This is the radar that we use. It's called RAXPOL, standing for Rapid Scan X-band Polarimetric Radar. The antenna moves around like a bat out of hell at 180 degrees per second. And when the radar spins around that quickly, you don't get enough samples to get good estimates of the wind velocity and the reflectivity. So what we do is we use what's called frequency hopping. We take the radar frequency and jump it about 11 times, and we make each jump be wide enough so that we're getting independent samples. It's as if you have 11 radar. It's really neat technique. It's been around for a while. Now, the need for mobile radars. We need to maximize the spatial resolution by getting close and personal. We get simultaneous visual observations. You want to see what you're probing. Also, you want to optimize the number of cases you have to study. You don't want to wait for the storms to come to a fixed site. You want to go out and be aggressive. The need for rapid scan is that the time scale of a tornado is only of 1 to 10 seconds. You can see that in the video. We have what we call the advective or orbit time scale. Time it takes an air particle to move around the tornado. That's its time scale. That's about 1 to 10 seconds. I'll skip down here to the last part. Why do we need polarimetric radars? And we use polarimetric radars because, for example, large raindrops flatten as they fall. And if you have a radar that has a part that's vertically polarized, a part that's horizontally polarized part's going to get more backscattered radiation than the vertical part. Also, hail tumbles and so on. And the various properties of the hygrometeors affects the polarization. And we can use fuzzy logic to identify the hydrometeor type and get a better understanding of the cold pool. I mentioned earlier, the cold pool is very important. We needed the cold pool to get the horizontal vorticity. And depending upon the type of hydrometeor, we may get a lot of evaporation or not much evaporation. So that's important. Also, we can distinguish debris from rain by looking at the polarimetric variables. Here's a time lapse of the formation of the El Reno tornado. This was a famous tornado that hit El Reno in 2013. And unfortunately, Tim Samaras and other people were killed in this tornado. And the Weather Channel vehicle was overturned. And we're at a safe distance away from the tornado. You can see as it forms, it develops an eye, a weak echo hole right there. And then we get out of Dodge. We get out of the way. This tornado was heading towards the southeast, and people were fooled, and then came back to the northeast. The hole in the center of the tornado is not like the eye of a hurricane. It's caused because raindrops and hail and debris are affected mainly by the centrifugal force in the tornado and not much by the pressure gradient force. So they get centrifuged out. And so we have a dearth of scatterers in the middle of the tornado, hence the eye. We can track the intensity of a tornado by looking at the difference between the strength of the wind maximum going away from the radar and that coming toward the radar. That's a measure of the intensity of the vortex. And what you can see here is a vertical cross section from 0 to 4 kilometers. Time runs to the right. Each of these tick marks represents 30 seconds. And what you see is that the tornado begins as a mesocyclone around 1 kilometer above the ground. That's the low-level mesocyclone. And then magically, a tornado forms 80 meters per second difference down here at the ground. Tornado forms at the ground. We have many observations like this. And then a little bit later on, a minute or two later, the tornado is advected upward by the updraft in the tornado, all the way up to 3 kilometers. We have observations that show these vortices going all the way to the top of the storm, to the tropopause level. Rather remarkable. So the thing we're learning is that tornadoes, we believe, begin after the low-level mesocyclone appears. They appear at the ground, and then they build upwards. Here's a time-lapse animation from the data taken every 2 seconds by our radar. This is reflectivity. This is a polarimetric variable called ρHV. I'll talk about that in just a second. What you see here, and if we can come back, we're looking off to the south of the tornado. It's moving to the northeast. There's the eye and a debris ball. That is what we call a weak reflectivity band. And that's due to friction behind what's called the rear flank gust front. I don't have time to talk about all these things in detail, I'm afraid. But this over here is ρHV. This represents the debris in the storm. You can see the debris circulating in a cyclonic manner, and then later you see a tail form producing like a comma. That tail represents debris ejection. That's debris that's coming out of the tornado aloft, falling down, This, by the way, was taken at 1 degree elevation angle, so we're right near the ground. Then the debris gets sucked into the tornado right near the ground. A little bit of dynamics. What happens when a tornado rubs against the ground? Above the ground, we have what's called cyclostrophic balance. We have an inward directed pressure gradient force. That inward directed pressure gradient force, what's that? Well, we can associate the wind and the pressure with each other. One doesn't cause the other. They both occur together. And the reason why we have a vortex is that the air is always accelerated to its left or to its right, perpendicular to its motion. So we get a vortex. That also means that in the reference frame of the tornado, we have a centrifugal force which acts outward. When those two are in balance, we have cyclostrophic balance. Now, at the ground, however, the air rubs against the ground and it's slowed down. Friction slows the air down. So since the centrifugal force is proportional to the square of the wind, remember 801, that we have an imbalance now. This centrifugal force is less than the pressure gradient force, and so the air accelerates inward towards the center. So there's cyclostrophic balance. Pressure gradient force acts inward, centrifugal force acts outward. As we get near the ground, the centrifugal force acting outward decreases, pressure gradient force acts inward, and the air, since this is happening at all azimuths, the air converges in the middle and it rises into a jet. Do you remember an old PSSE movie that I think we saw in physics? You stir leaves in a teacup and they gather near the center. That's the same effect due to friction. Now I can verify this. I was in a helicopter looking at the damage from the Moore tornado. There's the tornado track. And look at these trees that are all uprooted. They're all leaning towards the tornado track. They're not spinning around the tornado. They're leaning in. So that means that when you get near the ground, the air is really converging in a tornado. Most of the rotation is appearing just above the ground. It's somewhat of amount of controversy as to how deep this convergent layer actually is. There's some evidence it may only be a meter or two deep, other evidence that it might be 10 or 20 meters deep. With a radar, we can determine the profile of the wind. Let's just look at this observation here. This is the center of the, this is where the radar is. That's going out. And you can see that the wind increases linearly in wind speed up to a certain point and then drops off, almost like 1/r. We have many observations like this. And so the tornado is modeled as what we call a Rankine vortex, and that we have solid body rotation in the tornado and no rotation outside of the tornado. See? Now, the convergence increases the vorticity, which is driven by the buoyant updraft. And there's the conservation of angular momentum skater analogy. The air is being driven by the buoyancy, the vorticity increases as the air is drawn in. However, it turns out that in a vortex, which is solid body rotation, turns out it's stable with respect to horizontal or radial displacements. If you squeeze it and let go, it's going to oscillate, producing what's called a centrifugal wave. It takes a lot of work to get the air in. In fact, it takes infinite work to make it go into the center. So you can't have an infinitely strong tornado. How much work is expended through the buoyant updraft is what's called the thermodynamic speed limit. That tells you what the maximum speed you can get in a tornado from the amount of buoyancy there is in the updraft. However, it turns out, and we found this out with our measurements, the speed limit can be exceeded because of friction. Near the ground, the air slows down, the pressure gradient force makes that air accelerate towards the center. That's due to friction, and you can get an even stronger tornado. The wind speeds at the surface are due in part to the rotational speed of the tornado in translation. So you can have a really strong tornado that's not moving very quickly, or you can have a very weak tornado that's moving very quickly and get the same wind speed. So when you look at the damage and estimate the wind speed, you may really have a weak tornado that's moving quickly rather than a strong tornado that's just sitting there. I'm going to try to finish this off here in a minute. This is a vertical cross section through a tornado using a different radar. This is a 3mm wavelength radar rather than the 3cm wavelength radar I talked about earlier. That's at what we call W band. At W band, we get a lot of attenuation through rain. The radar doesn't see very much, but it has incredibly high resolution. And I want you to look through the scan number 6 through the tornado. That's this one here. The inside of the tornado is in fact hollow because all the scatterers are being centrifuged outward, except right near the ground where the air is converging in. And there you can see scatterers. Kind of neat. These are the wind speeds in the tornado as a function of height. This is meters above the ground. And for scan number 6, you can see that at about 50 meters above the ground, we're getting wind speeds that are almost 80 meters per second. So that's 150 miles per hour, maybe a little more. But the winds drop off as you get right near the ground, and they drop up above that. So the maximum wind speeds are not at the surface, they're elevated just a little bit. I'm running out of time here, so let me just very quickly show you that we can look at the amount of flow coming into the tornado versus the amount of flow going around the tornado. What controls this? I have no idea. You can control this in your model and in the vortex chamber. In the real world, I don't know how this happens. But we can increase the amount of swirl. As we increase the amount of swirl relative to the amount of radial flow, what happens is the vortex gets stronger and stronger, and we get relatively low pressure, which sucks air down in the middle. So instead of getting an updraft, we get a downdraft. And now we have something which is kind of curious. Look at what happens. We get a downdraft and an updraft converging with each other. And we get something that's called vortex breakdown. And the vortex becomes incredibly turbulent at this point. This turns out to be an analogy to what's called a hydraulic jump. For any of you who are familiar with fluid flow, if you've ever watched water come down a waterfall or go over a rock, it goes over the rock, it hits the ground, and it becomes turbulent, and then the height of the water jumps up. If you increase the swirl even more, that downdraft makes it all the way to the ground, and the vortex broadens, and we get very strong lateral shear. That leads to an instability that leads to these multiple vortices, these tiny little tornadoes within the tornado. And there's a picture of one instance. Each of those is a tiny tornado within the larger tornado. And these can do incredible amount of damage. Here's some radar data we took that shows one of these rotating around the main tornado. The main tornado can be seen through the red and purple. That is flow away from the radar, flow toward the radar. Here we have green and yellow. That represents the small scale vortex. We can track it as it moves around the main tornado, and it moved at 78 meters per second. That mini tornado within the tornado is moving over 150 miles an hour. And this is what we believe killed Tim Samaras and what flipped over the Weather Channel vehicle. The ground relative speed was 135 meters per second, which is 300 miles per hour, which is EF5. This is as strong a wind as we've ever measured at the ground in a tornado. There was one other measurement that Josh Werman made that was this strong, and this is another one. Never been one stronger. I'm going to skip this and get right on to the very end. And let me just talk about climate change. How will tornadoes be affected by climate change? Well, we know there's going to be warming. And if there's warming, the air can hold more water vapor. And so we have the potential for a lot stronger buoyant updrafts, but that's if the air doesn't warm up aloft too much also. If the air warms up aloft also, then it turns out that the updrafts won't have any change in buoyancy. In fact, the buoyancy may decrease. So that's a big unknown. Now, we know that in global warming scenario, the most of the warming occurs in the polar regions. The polar regions are warming up a lot more rapidly than the equatorial regions. So that means that there's going to be a decrease in the pole to equator temperature gradient. Now, it turns out that the vertical shear in the atmosphere is related to the pole to equator temperature gradient. Stronger the temperature gradient, stronger the vertical wind shear. During the winter time, when we have extreme temperature gradient between a pole and the equator, we have very, very strong vertical wind shear. We have a strong jet stream. During the summertime, temperature gradient gets a lot weaker, and the jet stream migrates poleward and becomes weaker. So if the strongest tornadoes come from supercells, that might argue that we will get fewer supercells. So that might argue that maybe we'll get fewer tornadoes. But wait a minute, there's more. If you change, there could be a change in the jet stream pattern. It turns out that the jet stream pattern is affected by the vertical wind shear through a process called baroclinic instability. And the most unstable wavelength will vary as the vertical wind shear does, which is also the same as saying it will vary as the pole to equator temperature gradient changes. So if you look at the jet stream pattern, for example, during the winter time, you might see 5 or 6 waves around the pole. That will change if the baroclinicity decreases. So that means that the area of highest shear may shift around and the locations of high tornado frequency will change. And what you can do is run your numerical model with a global warming scenario and see what happens to the jet stream, see where the environment is best for supercells. Will it change? And it probably will. Another thing we have to consider is that if there's weaker shear, that means that the westerly winds in the jet are weaker, and it's possible that cold air from the poles are more likely to enter the United States with big cold outbreaks. That's kind of an irony of global warming. The atmosphere as a whole will warm up. The pole to equator temperature gradient will weaken, but that might allow more of the cold air that's locked up at high latitudes to penetrate into mid-latitudes, and that would work against tornadoes. I don't know. These are just ideas that I'm throwing out. I have no idea what's going to happen, but what I do know is that it's not clear what's going to happen. So my last slide, some of the future and ongoing work. When we look at tornadoes with a radar, we're tracking the motion of the scatterers. We're hoping that we're tracking the air, but if there's debris, the debris is not moving along in the same way that the air is moving along. We need to separate the two. And we can do that by calculating the Doppler spectra. Turns out that if you're using a very rapidly scanning radar, this is something that's very difficult to do. And we are in the process of trying to do that. We have a grant to do it. And we weren't able to go out last year. And the year before that, we weren't successful. So we're going to try again this year, we hope. Another possibility is to use a Doppler LiDAR rather than a radar. LiDARs have ultra high spatial resolution, and you don't have to worry about ground clutter. These are false, well, not false, but contaminating radar echoes that you get from a part of the beam that's not looking directly in the direction that the radar is looking. Also, you have to be within 5 or 6 kilometers. We used a LiDAR several years ago, and every time we went out, we couldn't get within 10 kilometers of the tornado. We were very frustrated. Finally, under construction is what's called the PAIR, or polarimetric atmospheric imaging radar. This is a completely electronically scanning radar that operates at 5 centimeter wavelength, and I don't have time to talk more about it, just to say that it's a super radar. And
Thank
that
you.
is it. Sorry, I went over a little bit. We started a little late, and
It's very interesting, and people have questions, and I'm told we can run over past noon if you can stay past noon. So there are 3 questions on chat. Let me start with those. And if other people have questions, please go to participants and click raise hand, and then we'll take those in order. So the first question is, and I apologize for the name, Banerjee Shema. Is that person here?
Yes, Shamadas Banerjee, viewing from Arlington, Virginia.
Go
Yes.
ahead.
Well, my question was basically, I think, addressed by Dr. Bluestein, which was about how climate change is affecting tornadic activity. And we are seeing more frequent tornadoes even in Virginia, which we have not witnessed in the past. So I'm wondering how this climate change is contributing to this.
my short answer is I don't really know. It's possible that the tornado frequency has gone up in the last few years. That might be related to a change in the jet stream pattern due to global warming, or it could be just something that's naturally occurring. I don't think that the record is long enough to say for sure. Let me say, for example, that Karen mentioned the Worcester tornado back in 1953. That was a huge tornado. That was very, very unusual. That was preceded the day before by a major tornado in Flint, Michigan. If that were to happen today, if Worcester were to get hit by a big tornado like that, and then the previous day Flint, Michigan were to have gotten hit by a big tornado like that, then you could ask the same question. Wow, maybe global warming is causing that, but I think it's too difficult to attribute that. If it turns out that you look over the next 10 years in Arlington, Virginia, not necessarily Arlington, Virginia, where my sponsors at NSF are, by the way, we don't want any problems there. Then we could say yes, maybe something is in fact changing. This could just be sporadic events. Also, I'd like to say that right now with cell phones, people can take spectacular videos with cell phones. Back in the olden days when I started out, there was no one out, hardly anyone out chasing storms. And when they did, they may have had a film movie camera. People crowd the streets. We sometimes can't find a parking spot for the radar truck when we're chasing tornadoes to get data. So it's very unlikely that an event's going to happen and not be reported. 40 years ago, it's possible a tornado could have hit Arlington. Without a Doppler radar, you wouldn't have known that that was a supercell. Someone may have reported some tree damage, and that would have been it. Whereas now, people are out with their iPhones, getting videos of the tornadoes. They're on the news almost instantaneously. So I don't really know.
Quick follow-up question is the big data and artificial intelligence, is yielding results in many, many fields. And I wonder if this has been applied in analyzing tornadoes, and
Yes,
you can glean something from that.
Yes, that's a very good question. I do have a few colleagues who are in fact doing this right now. And there is some hope that they may be able to pull something out of the data. This is something that will be very useful in the future for weather forecasters. But for me, it's very unsatisfying because I like to be able to look and see there's a clear physical link between some parameter in the atmosphere and a physical process. If you, for example, look at 1,000 supercells and look at the environment and use artificial intelligence to determine what mix of parameters are most likely to produce tornadoes, that will be very useful from a practical standpoint. But for me, that's going to make me scratch my head and try to then figure out, well, what's really going on here? So
Okay.
it's challenging. It's going to happen, and people are just starting to do that right now. Yes.
Thank you very much.
Charles Carrion?
Yes. I live in New Mexico, and in the southern part of the state and eastern part of the state, it's fairly flat. We see a lot of dust devils. Is the same mechanism there? I mean, they're very short last. They may go up 50 meters or something like that, but
Yes.
it's the same mechanism.
Yes, dust devils are very similar to tornadoes. In fact, we have made measurements in dust devils and published them, and they look like tornadoes. They have eyes and so on. The difference between dust devils and tornadoes, the main difference is that tornadoes are driven by a buoyant updraft in a cloud, whereas dust devils are driven by a dry updraft. The air doesn't have enough water vapor to become saturated. So in both cases, it's buoyancy that's driving the updraft. Now, dust devils are probably a lot simpler physically than supercell tornadoes, because in the supercell tornado, you have a lot of different structural things happening in the parent storm, whereas a dust devil just needs to have the ground heated a lot relative to the air aloft and a little bit of wind, and you'll get a dust devil. Some dust devils, by the way, are strong enough to do damage. I've seen them do damage.
Thanks.
Thanks. Phil Byer, you there?
Yeah. Hey, Howie, thanks. This is really fascinating. I've got a question about the practical aspect of getting to a tornado to measure it when you don't know when and where it will occur. So what's the sort of the process that you have? How much time do you have to mobilize, and how do you do it?
Sure. We don't go blind. We don't go blindly. I mean, I began looking at the weather maps days in advance, of course, looking for the possibility there may be tornadoes. The night before, I look at the computer simulations, computer forecasts that come in. I look at the data, and I then have a very good idea as to whether or not the next day might be a day that we may be able to go out. I get up the next morning early, and I look at all the data. I look at the computer models, and if it looks as if the conditions are ripe for the production of tornadic supercells in an area that's within, say, 200 to 300 miles from Norman or wherever I'm based, we then leave and try to get into the general area where we expect that storms may form. If you watch the website of the Storm Prediction Center, they come out with what's called an outlook, which tells you whether over a broad area there's a possibility of severe weather. Then later on in the day, they may issue a mesoscale discussion saying, well, we might issue a tornado watch or a severe thunderstorm watch over this multi-county area. And we're generally within those watch areas. Sometimes we may go outside one. We may think we know better than they do. Sometimes we may end up not being able to get to a certain area. Then once the storms go up, if they do go up, sometimes they don't go up, in which case it's too bad. Nothing happens. Usually more than one storm goes up, and then you have the question of the lady or the tiger behind the door. Which storm do you go after? And then it becomes a matter of trying to look at the actual data in real time. We have access to the data in real time. Everyone does on your cell phone now. We look for the storm that we think has the greater or greatest potential. Sometimes that doesn't always work out because a storm may be blocking our travel route. There could be a traffic jam. There could be a flooded road, or there could be no roads whatsoever. We end up picking a storm. Then there's a certain amount of luck. Sometimes we are lucky enough to get to a storm just before the tornado forms. We set up the radar, let the storm come towards us. I say let the storm come towards us. And we collect a lot of data, and that becomes something which is worthy of scientific study, and my students get PhD theses. Sometimes we get there and the tornado is already there, in which case we have to fight for a parking spot. Sometimes it's unsafe to get to where we want to go, and we have to back off. So we're not out there just randomly looking at storms, looking for tornadoes. We have a look at the radar from the National Weather Service radar network. We have that in real time. So we see exactly where the storms that are out there are and how they're moving. We use everything we can possibly get our hands on, our dirty little hands. We use our intuition. We use the radar data. We use the observations at the surface. We look at the clouds, and we can tell some things about what type of clouds are out there and what they're going to do. So it's a mixture of art and science, but we've gotten very, very good at doing this over the last 5 or 10 years, simply because we have iPhones and laptops that are connected to the internet, even in the middle of nowhere. We have cell phone coverage almost everywhere we go, and we know exactly what's happening every second. 40 years ago, when I started doing this, we had no radar observations. We would have to play like Clark Kent and Superman. We would have to stop in payphones and call to someone back in Norman who would look at the data for us, tell us what was happening. Then we'd get back in the car and go out. It's not like that anymore.
Tony Picardi had a somewhat related question. Tony, you want to?
Yeah. So once you're out there, how close do you actually try to get to a tornado? And when it's coming toward you, and you look at the map and you say, "Whoa, I may not have a road to get out of here."
That's a good question.
Do you have an escape route?
Do I have what?
An escape route.
Of course. Well, 90% of the time we do. I can tell you a lot of stories, some for publication, others may not be for publication. Generally speaking, we try to get within 10 kilometers of a tornado. Beyond 10 kilometers, you can't see a tornado very clearly. Within 10 kilometers, you can get very high spatial resolution data with the radar. Okay, so we don't want to be farther than 10 kilometers. Sometimes we have to be. How close do we want to get? Well, I personally don't want to get within 3 kilometers of a tornado, simply because I have seen that debris can be flung out from a tornado several miles away. So I don't want to get closer than 3 kilometers. The optimum safe location, and one for which we can get very high spatial resolution data, is about 5 or 6 kilometers. So some of our best data come from 4, 5, 6 kilometers away. Yes, we've gotten data from 3 kilometers away, but generally speaking, that's when the tornado is moving at a right angle to where you're looking and not coming towards you. Let's see. Have we ever been somewhere without an escape route? And the answer is yes. And that's a story in itself. During the Reno tornado, the one in which Tim Samaras tragically lost his life, and so did some other storm chasers. Later on, after the storm left El Reno, it moved towards Oklahoma City. Now, I don't know how many of you are familiar with Oklahoma City. If you're from the East Coast, you're probably thinking this is some tiny little town. Population around Oklahoma City is about 1.5 million. It's spread out like LA. It's a very, very large area. This tornado occurred on Friday afternoon during rush hour. Trust me, rush hour in Oklahoma City on Friday afternoon, well, it's not as bad as New York or Boston, but it's not good. And when we got onto the interstate, there was no one on the interstate whatsoever, 0 cars, because the tornado crossed the interstate and people were not getting on the interstate. We, however, got on the interstate, we could see in our radar what was happening. And that was our safe route away from the tornado. And we could stop every time we wanted to. There were no cars. However, eventually we had to get off the interstate, I-40. When we got into Oklahoma City, we were heading back to Norman, and we had to get off I-40, and there was gridlock. And we got off the exit, and there was absolute gridlock there. And so we stopped, pulled off the side of the road at the intersection, and I said, well, let's scan the storm as it's coming towards us. We may as well get some data while we're here. Now, at the time, luckily, there was the potential for a tornado, but there wasn't an actual tornado. There was the potential for one. So we collected data, and then I realized that if the tornado were to come towards us, we had a problem because the traffic was just not moving. And so I scouted around and found a place where I felt that if we had to go, we could place our body down and hopefully be safe and be protected right near the ground. As luck would have it, an emergency vehicle came by with its lights flashing and recognized who we were and gave us an escort, got traffic to move. And this wasn't fair to the rest of the world. This is like Donald Trump getting the world's best COVID-19 care that most of us can't get. Well, we got get out of traffic protection, and we with the sirens flashing and the sirens blaring and the lights flashing, we got away from the traffic and got out of the way. But yes, I was very concerned there. Right now, during a tornado, there are a lot of people. Forget about rush hour. There were a lot of storm chasers out there. And there was an instance 2 years ago when we could not get the data we wanted to because the traffic was just stopped. You're out on a 2-lane highway out in the country, and storm chasers are out and they're stopped and you can't move. And it's very, very frustrating. And it's also very dangerous. So
I'm glad you're safe and you're still here.
thank you.
Howard Hoffman, you still there?
Yes. So Howie, in terms of global warming, it's obviously a very complicated story, whereas things like forest fires and hurricanes, you to see that global warming is making them worse. But isn't there enough data on like damage from hurricanes or the number of EF3 and above, or isn't there some data that's available that would show if there's any kind of a trend?
Yes. Again, you're venturing outside my area of expertise, and this requires a knowledge of advanced statistical techniques. We have a number of problems here. There are a lot of tornadoes, but the tornadoes that make the damage surveys are those that hit metropolitan areas or suburbs. So the big tornadoes, some of which we see over open country, one of my colleagues described them as doing minor damage to dog houses. You can't go out and come up with a good damage of the can't come up with a good estimate of the damage. Let me just give you a case in point. During the El Reno tornado, which killed people, and I showed you that our radar measured wind speeds of 300 miles per hour, that caused tremendous amount of controversy because when people went out and looked at the damage, they couldn't find any kind of damage that was consistent with wind speeds of 300 miles per hour. Now, then they started to argue, well, yeah, but the radar wasn't looking exactly at the ground, maybe. Well, no, the radar was looking pretty close to the ground. Well, there was an instance where the radar hit a little town west of Oklahoma City, and we have a wind measurement of 300 miles per hour, and they would not put into the record that this storm produced winds of 300 miles per hour. There are many tornadoes that occur in even more rural areas. So I would question the usefulness of those statistics. Now, it might turn out, for example, that there might be an increase in EF5 or EF4 damage in the last 10 years. it may also be true that many suburbs are growing rapidly around certain areas which have tornadoes, and they're making the statistics. They're biasing the statistics. Now, some of my colleagues have used statistical techniques which supposedly can account for these biases. I'm not well versed enough with these techniques to really evaluate whether that's true or not. One of my colleagues from another institution claims that there are now more tornadoes east of the Mississippi than there have been in previous years. And I was a reviewer of that paper, and I had problems because I didn't understand the statistical techniques that he was using. There's more uncertainty with tornadoes than there is with fires and hurricanes. Hurricanes do broad damage, and fires, I mean, for heaven's sake, you can see that there are more fires out there now. Are there more tornadoes of greater intensity? Tornadoes are maybe a kilometer or two across at most. They're going over areas where there aren't any people living. I don't know. By the way, Oklahoma City, the suburbs are expanding tremendously. It's like Los Angeles used to be. Used to drive between Norman and Oklahoma City, and you could see farmland. And now it's almost continuous houses. So it's more difficult. The bottom line is, I think it's more difficult to tell whether damage from tornadoes is increasing or not.
Howie, there are ways to build buildings, houses, whatever, that are somewhat more protected against hurricanes or maybe even against fires. I'm not sure. Is there any way to build that protects you better against a tornado?
Sure, if you have the money. A number of years ago, the Nuclear Regulatory Commission funded studies on tornadoes, and they wanted to be able to build nuclear power plants that could withstand the direct impact of a tornado. Yes, if you design a building that can take 300-mile-per-hour winds, you're in good shape. That's going to be very expensive.
Or you go underground.
Well, you go underground, but you can build a building above ground that I think can take a very, very high wind speed.
So there isn't much of it taking place. There's not much of it taking place, that kind of building.
No, I mean, I think that it's probably more cost efficient to just strengthen the building so maybe you can take 200-mile-per-hour winds and put a basement where you can run in case of the tornado. And of course, you're not even 100% safe in the basement. There have been some times where people have been in a storm shelter, and you open up the storm shelter and debris comes in, or you can have debris covering a storm shelter. I mean, you could die in your storm shelter. Nothing's completely safe.
Another question. Are more students coming into meteorology now because of the focus on weather and weather damage than earlier in your career?
Yes, I think that early in my career, a lot of people began to come into meteorology departments because of tornadoes. And we can show that in the 1990s, late 1980s, early 1990s, there was a tremendous increase in the number of people we had coming into meteorology. I think now there are fewer people coming in that are interested in tornadoes and more that are interested in climate change and climate modeling. So yes, there are a lot of people who are coming in now.
Earl, did you want to ask a question? Earl Whitcomb?
I'm curious. High pressure cells in the northern hemisphere, at least across on each side of the United States, rotate clockwise. Why do tornadoes rotate counterclockwise?
Very good question. If I can share my screen over here. again. First of all, most tornadoes in the Northern Hemisphere rotate in a cyclonic manner, but there are some that rotate in an anticyclonic manner. I had to skip over this. First, let me show you, go back to the most complicated slide I had that I probably shouldn't have shown. And let me see if I can find it. All right, hang on here. This is the easiest way to find it. This slide right here. Okay, so this is what a supercell looks like. Now, it turns out, what I'm going to say may sound complicated. We'll try to make this as simple as I possibly can. In this supercell, we produce these counter-rotating vortices aloft. That is a result of the tilting of horizontal vorticity, which is a result of the vertical wind shear. That vertical wind shear is associated with the temperature gradient from the pole to the equator. The relationship between vertical wind shear and the pole to equator temperature gradient is dependent upon the rotation of the Earth, in particular on the Coriolis force. It turns out that these type of storms preferentially will propagate to the right of the vertical wind shear. So Earth's rotation does play an indirect role. It is not the rotation from the Earth that is the source of the rotation from tornadoes. It works indirectly. Now, when you consider that the tornado itself comes from the low-level mesocyclone, when you look at this configuration of the supercell moving to the right of the mean wind and the mean wind shear, because you get the cool air up in here, not down in here, it turns out that that spin, that horizontal vorticity that's generated here, as it moves into the updraft, it gets tilted up, and it just so happens to be in a counterclockwise direction. There are, on some occasions, on rare occasions, supercells for which the left moving part is dominant, and those can produce anticyclonically rotating tornadoes. Now, having said that, it's possible to get two at once. And I have a paper out, a paper published in which we have shown numerous instances where there are counter-rotating tornadoes. This is an animation of the debris signature from the Reno Tornado. There's the main tornado, and you can see that it's rotating in a counterclockwise cyclonic manner. Down over here, you can actually see a anticyclonically rotating debris signature coming from a tornado. This is the Doppler velocity. Just focus your attention on this here. The red's going away, the purple's coming towards. That's the main cyclonic tornado. There's also a small anticyclonic tornado here, yellow to green. So we can also get anticyclonic tornadoes paired with the cyclonic tornadoes. If you consider the rotation of the Earth as a source for the vorticity in a tornado, it turns out that it will take much, much too long for that to happen. It doesn't happen.
Thank you. We have, I believe, one final question, and before we sign off, Shyama.
Banerjee. Shamadas Banerjee. Yes, it was about, well, I think we got the answer, but the question was about what is the safest place, when a tornado hits in a house.
Well, if you have a basement, the safest place is in the basement. You get down below the ground. If you can't do that, it turns out that inner bathrooms are constructed fairly well. And if you look at instances where houses are blown apart by tornadic winds, that sometimes the the bathroom areas, the shower stalls, for example, are left standing. When my wife can't go to a storm shelter, we don't have a shelter in our house in Norman. If there's plenty of warning, she gets in her car and drives to the university, and there's a shelter there, the basement of the library. Otherwise, she grabs one of my my biking helmets, and she goes into the shower stall, and it can bring something to protect her head. So that would be the best place to go. Stay away from windows.
Thank you.
Howie, thanks very much. That was fascinating. Thanks to all our viewers for joining us. As I mentioned in the beginning, we will have another environmental session approximately a month from now. I'm not sure yet whether it'll be Veterans Day or a different day, but the focus will be invasive species, otherwise known, I think, as weeds, by Rod Walker from Virginia. I've been fascinated by what he's been doing, so stay tuned for that. Thanks to Nancy Mims and Cardinal and Gray for hosting us and helping us. And stay safe, remember to vote, and see you again. Take care.
Bye-bye.
Thank you.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.